is that a huge disappointment for the scientific community? What would it be able to do that the LHC couldn't do?
It was a higher energy accelerator than the LHC, so it would have discovered the Higgs particle first, had it been running.
But the half-built part, is it useless now, or can they
I think
sort
they
of
filled
recharge
it
up again?
No, I think they filled it in. I mean, it was just half a tunnel, you know. So that's the thing. You can do these wonderful things for not a lot of money if you just do it over many years and have stable funding.
Yeah,
commit to doing it.
The filling it in part.
And you look at CERN as well. And people ask me now. I think the UK pays about $100 million a year. That's what the UK pays in. And it's about the same for Germany, same for France, and so on. And so people say, what do we get for that? I mean, first of all, it's not the whole budget of CERN is about the same as the budget of a medium-sized university. It's not a lot. It's about $1 billion a year or something, which is what a university has. So it's not a lot in the scheme of things. What's it done, though? Well, we invented the World Wide Web, as we've just said. A lot of the medical imaging technology that we use comes from CERN. It's pioneered the use of these very high field magnets, which is what it needed. So it's engineering at the edge. And engineering at the edge generates spin-offs and trees to get used in tools. So there's cancer treatment, so-called hadron beam therapy. So if you've got a brain tumour now, it's quite likely that you'll have one of these targeted particle beam therapies. Very highly targeted sort of chemotherapy. It's not chemotherapy, it's just radiation. We can target in a beam into your head and attack the tumour. And those are particle accelerators. So most particle accelerators today are in hospitals and in medicine. But they came from doing particle physics. So the spin-offs of these big experiments at the edge of our capability are always immense, which is why they were funded at these very low rates. But it's not just the knowledge, it's the engineering expertise.
That there is a practical application for everybody.
There always is. It's just finding out how to do hard things is usually useful, is the moral.
And it wasn't just the Higgs boson particle that you guys had discovered. What was quark-gluon plasma?
Yeah, so that's shortly after the billionth of a second after the Big Bang. So
Yeah.
you end up with a soup of quarks and gluons. So quarks are the building blocks of protons and neutrons, and gluons are the things that stick them together. So a proton has 2 up quarks and a down quark, and a neutron has 2 down quarks and an up quark, and so on. So they're the constituents, the protons and neutrons, which are the constituents of our atomic nuclei. So if you go to very high temperatures or high energies, then the protons and neutrons fall to bits, and you end up with a soup of quarks and gluons, and that's a quark-gluon plasma.
And it's insanely dense, right?
Yeah, well, very high energy. So you get that. So we've been exploring that because we don't only collide protons together. We can collide lead nuclei together or silver nuclei together at the LHC, and that's when you have these soups of nuclear matter, if you like, very hot nuclear matter, to explore that physics, that nuclear physics.
And I was reading something about the weight of that stuff. That, like a sugar cube, like what is the actual weight?
Well, it depends how dense it is. So the thing I remember is the sugar cube of a neutron star material, which is, I don't know how many, 100 million tons. I can't remember. Depends. So I don't know with the quark-gluon plasma. I don't remember.
There was something. There was one of the things after the discovery they were talking about the massive weight of quark-gluon plasma, and almost incomprehensible.
Yeah, I don't know the number,
but something crazy.
Yeah.
Now, once these, you got something? Oh, here it is.
40 billion.
Oh my God! A cubic centimeter would weigh 40 billion pounds. Good
cool.
Lord!
I didn't know that. I know David. I know David actually.
That's
University
so
of Birmingham. Yeah.
The densest matter created in the Big Bang machine. And what are they doing right now?
It's closed for engineering and upgrades. Yeah, I mean, one thing we're trying to do is, one of the things in particle physics is that you want as many collisions per second as you can generate. And we have a collision, we have what's called a bunch crossing at LHC. we can vary it, but it's something like 25 nanoseconds, depending on what. So it's really, we get a lot of collisions per second. And the more collisions per second you can get, the more chance you have of making interesting things like Higgs particles or whatever else may be out there waiting to be discovered. I mean, it's possible there are other particles out there discovered that could be within the reach of the LHC.
And if this one that was in Texas had gotten built and it was more powerful than the LHC, you'd have even more opportunity.
Yeah.
Now, when these things are created by these collisions, how long do they last?
Oh, fractions of a second. So the general rule in physics is the more massive it is and the more things it can decay into, the faster it will. So basically, the heavy things decay into light things. And so the stable particles are things like electrons and some of the quarks. The up quarks and down quarks are stable things. But so everything tends to decay very fast. So we're talking billions of years.
And how are they
Less than that.
How are they registering its existence? Like, what is the measure it?
So what you see, if you collide,
Hostile UAV in the
at
area.
the LHC we collide protons together. And protons have got loads of stuff in them, loads of gluons and quarks. So you get a big net. So most of it's a load of particles just spraying out. But sometimes when let's say a couple of the gluons bang together, and they can make something interesting, like a top quark or a Higgs particle.
What's a top quark?
A top quarks are very heavy. There's 6 quarks. So there's up and down, charm and strange, bottom and top. Now
Charm and strange?
Yeah. So strange was literally in the, what was it, the 50s, when we discovered them, someone said that's really strange. So it's a strange, a new kind of particle. So yes, we have 6 quarks. They're in 3 families. So the up and down are one family, and then the charm and strange are another family, and the top and bottom are the third family. And so we, for some reason, so the only particles we need to make up you and me are up quarks, down quarks, and electrons. But for some reason, there are 2 further copies of those, which are identical in every way except they're heavier. So there's the charm and the strange quark, and a heavy electron called a muon. And then there's the top and the bottom quark, and another heavy electron called a tau. And that's it. So there's this weird pattern that we don't understand. So it seems like you only needed the first family to build a universe.
Right.
Right. But for some reason, there are 2 copies.
Now, when
And the heavy ones decay into the lighter ones is the point. So when you make them, they're not around very long. And just to answer your question, what happens is that when they decay, they throw their decay products out into our detector. So we take a photograph of the cascade of particles that comes from these heavier particles decaying, and the trick is to patch it all up to see, to try and work out where everything came from.
Wow. Now, when they find these unexpected particles, then what happens? Then there's the study of them. Then there's then everybody gets together and go, okay, what the hell is that?
Yeah.
What is that?
So-
and what do we do?
So we want to know with a Higgs particle, we know what it does, because it gives mass. So it's fundamentally the thing that gives mass to all the other things in the universe at the most fundamental level. So electrons, for example, in the upper they get their mass from their interaction with the Higgs. That's why they're massive. That's another reason we exist. You know, we go right back. We wouldn't exist if there wasn't mass in the universe. And the Higgs is also that mass. I keep caveating it because then you get other sorts of mass that are generated, but the fundamental basic seed, as it were, is from the Higgs. So what we want to know is we want to know how that thing behaves, and so you want to study it. So you want to make a lot of them, so you can take a lot of pictures of it and study it a lot and see exactly how it does that. And so that's what we're doing. That's what we're engaged in at the moment. We're making high precision measurements of the way that particle behaves, so we can understand the laws of nature. And that is the laws of nature. How are those particles behaving and what are they doing?
But it is possible that some new form of particle, something else, could be discovered
Yeah,
that we don't know about yet.
Because we almost know that there are other particles out there in the universe.
We almost know?
So a thing called dark matter.
Yes.
So we look out into the universe, And we see that there's a lot of stuff there that's interacting gravitationally, but is not interacting as strongly with the matter out of which we are made and the stars are made. So it's almost certain that that's some form of particle, that fits beautifully. And we see lots of different observations, the way galaxies rotate and interact, and even the oldest light in the universe, the so-called cosmic microwave background radiation, we see the signature of that stuff in that light. So we think that there's some other particle out there. And to be honest, we thought we would have detected it, I think, at LHC. We have lots of theories called supersymmetric theories that make predictions for all sorts of different particles that would interact weakly with I think it's broadly seen as a surprise that we haven't seen them at LHC. So that just may well mean that either they're a bit too massive, so we need more energy to make them, and we just haven't quite got enough, or we're not making enough of them often enough to see them, which is one of the